Hello everyone, welcome to the OneClass channel. My name is Millan and I'm a software engineering student at Carleton University in Ottawa, Canada. Today, I'll be going over some commonly asked physics questions at both the high school and university or college levels. If you're interested in getting some help with your homework, or if you're interested in getting some tutoring, check out the links in the description below. Cool, so I'm going to switch my screen ASAP fast and we can start this physics experience. Okay, just move some things around. Okay, so let's get this party started. Whoops. Okay, so the first question that we got is an electric circuit type of question. So it is, we got the circuit here, and can't lie, this diagram is, let me redraw this diagram real fast to say this nicely. Okay, so we have a 1.6 ohms over here. We got a 3 ohm down there. Here we have a point Y. Here we have a resistor R. We don't know what the ohm level on that is going to be, but no worries. Here we have 2.1 ohms. And then we have two voltage sources in here. Now, it doesn't necessarily tell us which direction is their positive terminal or which direction is their negative terminal. So we're just going to make some guesses. Now I'm going to guess that they are going in opposite directions. And that is because if they were going the same direction, like it wouldn't necessarily make that much sense to have two separate voltage sources. So I'm going to say like one's forward and one's backwards. Okay, so sometimes you'll see voltage sources like this, where this is the positive terminal and this is the, whoops, not the other positive terminal, the negative terminal. That's a common way to show voltage sources, but I prefer this way because, well, it's just a little bit more clear. And when you get introduced to capacitors, capacitors are just parallel lines like this. That's a capacitor, and capacitors can sometimes get confused with voltage sources if you draw them this way. So that's why I recommend with this, the circular way. Okay, so let's say we have one with the positive to the right. And let's call that a 28 volt source. And in the complete opposite direction, we got a 6 volt source. Yeah. Okay, so this is going to be a little bit of a cleaner representation of the diagram that we have here. Okay, so let's move on. Let's see what the question is asking us. So find the resistance R. Okay, and the resistance here, and we're given the current as well. Now, I'm kind of confused as to why we would have two arrows for current. Current is only allowed to go in one direction. So we're just going to choose one of the directions. Now, considering that the voltage here, the net voltage source is going to be like positive towards the right, the current has to go in a clockwise direction. Okay, so let's say our current is going this way. I know it was originally drawn down there, but you know, it means the same thing when you draw it to the side here. And this is 2 amps of current. Oh, and the point between them, those two sources, is X. Okay, so given this, we got to find the resistance R. And the first thing that we can do with this circuit is we can make some simplifications by combining some of the things, okay? So since for part A of this question, we're not asking for X and Y, or there's no reason to, X and Y, these nodes are not relevant to part A, we can just redraw the circuit and compressing everything that we can. So the first thing we want to compress is we want to compress these two voltage sources into one voltage source. And maybe I'll put this in yellow. We want to make all of these resistors connected. Okay, now keep in mind, A small note that I want to say is that we're allowed to combine these series resistors. Like, we can't combine R into it because we don't know what R is, but actually we could, but we'll just keep R as a variable. Okay, my bad. So that's a perfectly reasonable way that we can deal with this. Okay, so here we have series resistors. And with our series resistors, we know that our equivalent resistance is just going to be the summation of all of the resistance, the individual resistors. Okay, so in this case, we got a 2.1, whoops, not 21, 2.1 ohms plus R plus 3 ohms plus 1.6 ohms. Okay, so our equivalent resistance of this whole circuit is going to be 6.7 plus R, 6.7 ohms plus R. Okay, so this is going to be our total resistance of the circuit. Okay, hopefully that should be nice and clear. Now with our voltage source, so equivalent voltage, I'll put it in red so it's, the colors match. Voltage source. Our equivalent voltage source looks a little something like this. Well, it's just going to be, since they're in series, we're just going to add them together. But keep in mind that the 6, we set it up so that the 6 is going the opposite direction, like their pluses are touching. So essentially, if we're trying to think about this in a more real life sense, the 28 volt is supplying current that the 6 volt is accepting. It's pretty much like the 28 volt is charging the 6 volt. So maybe an example of this is like, you know, you have a portable charger for your cell phone. Your portable charger is going to be at 28 and your cell phone is going to be like the other voltage source. Because your cell phone could still be a voltage source. It's just in this case, it's going to be a receiver. It's going to be like a drain, okay? So in this case, our equivalent voltage is just going to be our 28 volts minus our 6 volts. Because the 6 volt is absorbing the charge and absorbing the voltage. So 28 minus 6, quick math. I don't know about you, but I'm feeling 22 volts for our equivalent voltage. Let's draw a rectangle around that. So given our equivalent resistance and our equivalent voltage values, we can redraw a simplified circuit. So we have our 22 volter here. And for Req, we have 6.7 ohms plus R. .7 ohms plus R. And this is going right back into the source because everything else was just compressed. And our current going through here, as was the same before, I is equal to 2 amps. Okay, so this is going to be our complete circuit diagram. Pretty neat, or a simplified version of this. So, given that this is a fairly simple circuit, we can use the power of Ohm's law to solve for R. The R variable is what we're looking for here. So we know that Ohm's law is V equals I R. And we want to isolate R, so we're going to do V over I is equal to R. Okay, so let's sub in our numbers. Our V, 22 volts. I, 2 amps. And this is going to be equal to 6.7 ohms plus R. Okay, now just doing some quick math. 22 divided by 2, that's 11 amps. And let's bring the 6.7 to the other side. Minus 6.7 ohms is equal to R. And with some quick math, that will be 4.3. 4.3 ohms. Yep, exactly. So that's got to be the answer here. So our equivalent R that we found, or the only R value that we could sub into here, assuming this is the proper arrangement of the voltage sources, in that case, R would have to be 4.3 ohms. Okay, so, yeah. Let me just write that here because we don't have a given solutions to verify, so I'm pretty much making it as we go. So the R value is 4.3 ohms, assuming V sources are opposite. Okay, cool. So that addresses part A of this question. Now we gotta move on to part B. And part B is asking us for what is the potential difference between VXY and VY. Now, this seems like a formatting situation. I think it's really just asking us what is the potential difference between point Y and point X. Okay, so let's actually redraw the circuit, but we don't want to like when we redraw this, we're only going to compress the left two, and we're only going to compress the right two, but we're not going to compress this, the voltage sources. Okay, so I'm going to do a partially redrawn diagram, and we know that R is going to be 4.3, so that's good to keep in mind. So here we're going to have our 28 volt source, 28 volts. Point X is between that and the other voltage source that was 6 volts. Okay, and on the left side here we have R, let's just call it RL for R left, and that is going to be equal to the sum of the two on the left, so 1.6 plus 3. Equals 4.6 ohms. Nice and straightforward. Okay, and on our right side, let's call that R for our right side. That will be 4.3 plus 2.1. And that corresponds to 6.4. And between them is the point Y. Okay, so now that we have this, what we really want to do is find the voltage between them. So what's good? A good method that we can use to address this situation is to find the node voltages individually, and you know, just compare the node voltage of Vx minus the node voltage of Vy, and that will give us the potential difference between them. So as we do a node voltage analysis or nodal analysis, the first thing that we want to do is establish a ground node. Okay, now you can establish your ground node anywhere you want, but I think a very convenient place is to put it right before the voltage source is, and that's just going to make our calculations a lot easier. So let's call this our ground node right here. Ground, and this corresponds to 0 volts. That means that, you know, as we progress through the circuit here, if we cross this 28 volt source at point X, you know, we went from 0 volts, and then the voltage source of 28, point X, node X has to have 28 volts. Okay. Oh, another thing to keep in mind is that we have a current of 2 amps going this way. I equals 2A for 2 amps. Okay, so we have 28 volts at point X. Now immediately after that, 6 volts are taken away, and they're being absorbed or taken away by the 6 volt other source. Okay, so at this point right here, we have to have 28 minus 6. So at this point here, let's call that, maybe let's call that point A. we could say that this is going to be 22 volts, which came from 28 volts minus 6 volts. Okay, so now that we have this, we are also looking for the voltage drop between point A and point B. So we can represent that with, I mean, not point A and point B, point A and Y. And once we find Y, that's all we really need. So VAY. Now we can find this pretty quickly by doing Ohm's law. So I, R, subscript R. So that's going to correspond to 2 amps. Oops. 2 amps multiplied by 6.4 ohms. And this corresponds to, quick math, 12.8 volts. Okay, so we know that right here, point Y, VAY, another way that we can write that is VA minus VY, meaning that if we're trying to isolate VY, this will just be, VY is just going to be VAY minus VA. Whoops, I actually got the order wrong. Okay, you want to go from your destination minus your starting point. Okay, that was almost a catastrophic error, but we caught ourselves, or I caught myself, so we good. All right, it's always destination minus source. So VY would just be VAY. No, man, I'm tripping. I actually had it right the first time. It's VA minus VY. Okay, so if we wanted to isolate VAY, it's going to be VA minus VAY. Which makes sense because that's the voltage that is absorbed by this is VAY, and we just calculated that. So before it was 22. 12.8 was lost as we crossed there, so immediately after that it's going to be VY, which is what we're looking for. So this is going to correspond to 22 volts minus 12.8 volts. And the result of that is going to be 9.2, I think. Yeah, 9.2 volts. Should probably be asked. I'm gonna verify that with my calculator because you can't always trust yourself, even with fairly straightforward math. 22 minus 12.8. Yeah, 9.2. Cool. So this has got to be the voltage at point Y. But that's not the end of story. The end of story, what we're really looking for, is the potential difference between point X and point Y. We know that point X has 28 volts and point Y has 9.2 volts. So our voltage VXY, which is the difference, the potential difference between point VX, between node X and point Y, this is just going to be VX minus VY. In this case, 28 volts minus 9.2 volts. Okay, so 22, nope, not 22, 28 minus 9.2, that's got to be 18.8. So VXY, 18.8 volts. Yep, and that would be the end of story. Cool, so that would address part B, so I'll write that in. Potential difference between X and Y is 18.8 volts. No solution above to verify. Cool, so that was our little electric circuit question. So that was pretty fun. And yeah, we can call it a day on that one. Okay, so this is the next question that we have on the menu today, and it is asking us, given a 3,400 kilogram spacecraft that is in a circular, and that's important, a circular orbit, 1,100 kilometers above the surface of Mars, how much work does the spacecraft engines need to perform to get the spacecraft to move in a circular orbit that is 4,000 kilometers above the surface? Okay, so maybe it'd be helpful to kind of have a diagram to visualize this. So imagine here we have Mars. Maybe we'll be there one day, hopefully. I don't know if I'll go though. And we have a heavy spacecraft. Let's call this our spaceship. Speedy spacecraft. And it is going in a perfectly circular orbit. And orbit 1 is 1,100 kilometers. Okay, but the engines, if you want to you know, get farther away, you kind of gotta like crank up your engines, and you would follow a path like this until you finally get to your circular path. I know this don't necessarily look like it's circular, but pretend that it is. And this distance shall be 4,000 kilometers. Okay, so we have to figure out how much work is required. To increase orbital radius. And hopefully it's moderately clear that we're definitely going to need to put work into this. Otherwise, like, you'd be falling into towards Mars if you were not putting work into this. You have to increase the total energy in the system by doing work to accommodate this change in orbital radius. Okay, so let's write out our givens for this question. So we are given the mass of the spacecraft. So let's call that M, R, maybe R for rocket. 3,400 kilograms. We are also given the initial orbital radius. So let's call that big R, R1, and R2 will be our second. R1 was 1,100 kilometers. Another way that we could write that is 1,100 times 10 to the 3 meters. And it's always good to convert your stuff convert all your numbers into base SI. It will make it so that you don't need to deal with these prefixes inside your calculations, because those can be quite painful to deal with. Okay, so the next question, the second radius is going to be 4,000 kilometers, and that's above the surface. Okay, so that's very important. So that is 4 times 4,000. Oops. Times 10 to the 3 meters, and we could also rewrite these as like you know, having bigger powers and just putting them more into the, like, raise the power of 10. So this could be 1.1 times 10 to the 6 meters, and this can be 4.0 technically, times 10 to the 6 meters as well. Okay, so these will be our distance values, and what's important is that we're mentioning our distances as they are above the surface of the Earth, of the Mars, and we actually really need to know the radius of Mars as well. Okay, so fortunately, we have some other values of interest here, and if you were to encounter a question like this on a test or an exam, you would definitely have to have these given. Otherwise, this would be impossible to solve. Or you would not be able to come to a numerical answer. You could come to an algebraic answer, but typically you want to have a numeric answer. Okay, so our mass of Mars is going to be, let's call that big M and subscript m for mass of Mars. That is going to be 6.39 times 10 to the 23 kilograms. That's pretty heavy. A lot heavier than me, but less heavier than our planet. And the radius of Mars, so let's call this Rm for radius of Mars. That shall be 3.39 times 10 to the 6 meters. Okay, so to address this question, given all this, what we really want to think about is how we can relate the concepts of energy, potential energy, and orbital speed and kinetic energy to this. Okay, so we know that our conservation of energy equation, we can set it up like this. We know that our initial potential energy plus our initial kinetic energy plus the work that our rocket ship has to do is going to be equal to our final potential energy F for final plus our final kinetic energy. The reason that work is on the side of the initial, I'll write this initial and final. The reason that the work is on the side of the initial is because we're starting at our initial. Once we add that work, that's when we're going to get to the energy of our final. So that's why we have it like this. Okay, so oh, another thing that I need to mention, or actually, okay, we'll get there as we proceed. We're trying to solve for W. So let's actually get these equations out, or convert these terms into equations. So we know that gravitational potential energy this is negative, keep in mind the negative part, that's quite important. Yeah, so it is negative g, which is a constant, times the two masses multiplied together divided by r. And r in this case, do not just say it's the radius. It is not just the radius, it is the radius plus the additional altitude that you have. So this is distance between centers of mass. Okay, the next component that we need is kinetic energy. Which is 1/2 mv squared, but we need the velocity, right? We have the mass of the rocket ship, so lil m is gonna be the kinetic energy of the rocket ship. So that's cool and all, but we also need the orbital velocity. Now, it mentioned in the question that we have a circular orbit. So given that we have a circular orbit, that can give us, that's a very good clue, because we have an equation that is related to orbital speed, which is like this. So our velocity is equal to the square root of our gmm over r. Wait, not mm, it's just gm, right? And the r is the same situation as above. Do not get it confused with the altitude in terms of how far you are off the surface. You have to keep in mind that the radius of the planet itself has to be considered, because it's the distance between the centers of mass. Okay, so given the orbital speed as this equation, we could actually rewrite the kinetic energy equation. 1/2 m multiplied by the square root of gm over r squared. And we could also rewrite this as 1/2 gmm over r. Okay, cool. So given this, we can substitute out all of these symbols in our conservation of energy equation, and we can start subbing in our equations, and then we can do some algebra and solve for the work eventually. Okay, so we're going to have negative gmm over, now on the downstairs here, we have to keep in mind that this is the radius of Mars plus the initial altitude. Okay, so this is going to be rm plus r, I think we called it r1 up there. Yep. Plus r1. Okay, and then we have our initial kinetic energy. So that is 1/2 m times g mass of Mars over the initial distance, so the initial altitude, so that's rm, plus r1, yeah, okay, cool, plus w for work is going to be equal to our final kinetic energy, or our final potential energy, which is gmm over rm plus r2, keep in mind r2, plus 1/2 g big M little m over rm plus r2. That's in brackets and that's in brackets. Okay, so if we wanted to isolate w for work, we would bring a lot of the left side stuff over to the other side. So we just copy over the right hand side stuff to make this a little bit easier. Copy pasta. Okay, and I'll do the same thing here. It's just I'll need to flip those signs. Copy pasta. So from this this term right here brought to the other side is going to be plus. Whoops. And that's going to be minus. Plus this guy minus this guy. Okay, so we could just sub in our numbers now, but we could actually make our calculation a little bit easier if we do some factoring out. So, whoa, I think I lost the G up here. So all of them seem to have a G big M little m on top. So we can factor that out. Is equal to G big M little m. And all that would be left is negative 1 over Rm plus R2 plus 1 over 2 Rm plus R2 plus 1 over Rm plus R1 minus 1 over 2 Rm plus R1. Okay, this is going to be a lot easier to deal with, but we can even factor things out a little bit. We can factor things out one other level. So you see that these two terms here share Rm plus R2. These two terms here share Rm plus R1. So we can refactor this into GMM over 1 over Rm plus R2 multiplied by negative 1 plus 1/2, okay, plus factoring out the 1 over Rm plus R1, and this will be 1 minus 1/2. Yeah, nice. Okay, so now we can sub in all the numbers that we need. So bear with me, this will be a big calculation, but as long as we can type things into our calculator, there's nothing to worry about. So we have big G, which is a constant. Don't have it off the top, so I'm going to get it from here. 6.67 times 10 to the negative 11 times the mass of Mars. So the mass of Mars, it was given as 6.39 times 10 to the 23. Then we got the mass of our spaceship itself, and I think that was 3,400. Yep. Okay, and here we're going to have 1 over Rm, so that's the radius of Mars. That's going to be 3.39 times 10 to the 6. Plus our final altitude, which is 4 times 10 to the 6, 4 megameters. Okay, and that is multiplied with negative 1/2. That's minus 1 plus 1/2, so that's going to be negative 1/2. Okay, and then we're going to add that with 1 over, and this is going to be the radius of Mars. That's going to be 3.39 times 10 to the 6 plus the radius, the original altitude, 1.1 megameters. And this will be times positive 1/2. Okay, big equation, nothing to be worried about. So I'm going to do this in steps because these calculations are pretty fragile. So one wrong button press will crash the boat. So you definitely don't want to do that. It's better to be safe than sorry. Okay, times 10 to the power of negative 11 times 6.39 times 10 to the power of 23 times 3,400. Okay, so I got 1.449 times 10 to the 17 out here. Okay, now in there, I got got 7.39 times 10 to the power of 6, and that's on the downstairs, times 0.5 times negative 6.766 times 10 to the negative 8 plus, okay, now we have 4.49 times 10 to the power of 6. All of the downstairs divided by 2. And I got 1.114 times 10 to the negative 7. A little bit larger. But that is expected because the positive term has to be bigger than the negative term. Otherwise, we'd have negative work, and that makes no sense. We have to have positive work for this to work out. Ha, pun intended. So let's add these two beautiful things together. And multiply it with our thing out front, the 1.449. And my final calculation for this was the work is equal to 6,332,611. It's like I'm giving out a phone number. 304 joules of work. Okay, and another way that we could write this is originally we were given like 2 significant figures, or even 1 significant figures. Another nice way that we could write this is to 1 significant figures. And the 1 significant figures is just because of the 4,000 kilometers. This will be 6 gigajoules. It could be, or you can say like 6 times 10 to the 9 joules, or 6. Wait a minute, that was a 6. 6 gigajoules. I think it might be better to write it as the times 10 to the 9 though, because the G kind of looks like a 6. Okay, hopefully we came to a similar solution here. Exactly, precisely the same answer here. We just need to do the significant figure stuff, but otherwise, everything looks good. So that's a question well done. Very good. Awesome. Okay, so this is the next question that we got on the menu today, and it is asking us the distance from Earth, that's where we are, to Polaris, and that's a star that's very, very far away. In the night times, maybe you'll be able to see it. So the distance between us is 8.762 times 10. I'm going to assume what that means is times 10 to the power of 18 meters. Okay, so let's actually draw a diagram for here. So let's got our Earth. Hopefully we've all been here at least once. And our distance between us and Polaris. Polaris is a star, so let's draw it as a star. So the distance between us is going to be 8.576 times 10 to the 18 meters. And we're going to assume that this is just a formatting issue. How long would it take to disappear from our vision if it were to, I think that means burn out today? Answer in unit of years. Okay, so essentially, when we look in the sky and see stars, we don't actually see them. We see where they were. Okay, because light takes time to travel, like even this camera. This camera is not seeing me right now. There is a minor delay for the light to bounce off. You know, light comes from my lamp, bounces off my head, and bounces back into the camera. It takes time for that to happen because light is not instant. Light has a speed, very, very fast, but it still has a speed. So, you know, here it's going to be maybe like picoseconds, like so small that it's pretty much instant. But when you look at distances that are, you know, the like spatial distances, like spaces, like actually what I mean by like in space, those types of distances, light actually does take a while to travel. I think it takes sunlight about 8 minutes to reach Earth. So if the sun were to suddenly just, you know, peace out and didn't want to be, it wasn't all sunshine and rainbows anymore, and the sun just dipped, it would take about 8 minutes for us to even realize that it happened, because that's how long it takes for light from the sun to reach us. So the light is a lot closer to us. I mean, the sun is a lot closer to us than Polaris. So this effect will be magnified by a lot. So we expect that this is going to take some delay. Another interesting thing about this is if we were to somehow teleport very, very far away and you looked back at the Earth, you could see yourself in the past, possibly, because of, you know, if you were to somehow travel faster than the speed of light or get to a distance faster than light can, you'd see in the past. That's a very interesting thing to think about. Okay, but that's kind of going beyond the scope of this. We know that the velocity of light, speed of light, we represent it with the letter C. And that's just the way it is. Okay, and the value that we're using here is 3 times 10 to the power of 8, which is typically what you're going to use, right? Sometimes you use 2.99 if you need extra precision, but 3 is fine. So 3 times 10 to the 8 meters per second. So this is the speed of light, and we want to find the time that it will take for light traveling like this to travel this distance. So we know that distance over time is going to give us our velocity. We can also write this as v. C is just what we typically use because the speed of light is so commonly used, but in general it's better to use, or in this type of situation it makes more sense to use v because we're thinking about more of a velocity thing, and we're not going to worry about like time dilation and all that. Don't worry about it. That's Einstein. Okay, so here we want to isolate t. So to isolate t, we're going to multiply both sides by t and divide both sides by v. So d over v is equal to t. And let's sub in our numbers. So our d value, that's our distance, d, 8.576 times 10 to the 18 meters divided by the speed of light, 3 times 10 to the 8 meters per second. Okay, let's do some quick math to figure it out. Quick math by asking our calculator. 8.576 times 10 to the power of 18, all divided by 3 times 10 to the power of 8. And my result for this calculation is 2.859 times 10 to the 10 seconds. Okay, so I'll just represent that with an S. Okay, so that's the time that it will take, but it asks us for our answer in years. So we have to convert this into years, because I know that that's a long time, but when we think about it in years, we can more contextualize it, like how many human lifetimes is this going to take? Okay, so given that we have 2.859 times 10 to the 10 seconds, we're going to do a unit conversion process to get to years. So we know that if we multiply, we have to divide by 60, so 60 seconds per 1 min. And we know that we have every 1 hour we get 60 minutes. Okay, and hopefully you can see like these units canceling out and why that works out. Then we're going to divide it by 24 for 24 hours for 1 day. And we're not going to worry about like leap years and all that. Let's just do 365. Technically it would be more accurate to do 365.246 or something like that. But we'll just use 365 and not worry about light years. I mean, not light years, leap years. So 1 year is 365 days. Okay, so in years, we're just going to divide by 60, divide by 60, divide by 24, divide by 365. Okay, so let's do that math ASAP fast. Take the number that's stored in the RAM of my calculator, divided by 60, in brackets divided by 60 times 60 times 24 times 365. And my calculation for this is 906.47 years. Approximately. Given that we only had one significant figure in, for our speed of light that we use, we could technically only say 900 years. So 1 SF. So, if you're very lucky, if Polaris was gone, 800 years ago, my grandchildren might be able to realize it. So it takes quite a while. Hopefully, we got a similar answer. Yep, they got pretty much the same calculation, maybe with some rounding errors, but that's nothing too concerning. So yeah, this question is good. So the above solution is good. Awesome. Okay, so here we have the next question that we have on the menu today, and it is asking us about radio stations. So radio stations are usually identified by their frequency. When a radio station in the middle of the FM band has a frequency of 95.3 megahertz, the speed of light, and okay, so the speed of light, the name is kind of misleading. The speed of light is all electromagnetic radiation, and radio waves do count as electromagnetic radiation, so they will also move at the speed of light. So this is the speed of light, and we need to find out the wavelength of this speed. Of this radio station. Okay, cool. So let's look at our givens in this question. We are given our frequency is 95.3 megahertz. And that is actually a very reasonable number for a FM radio station. You've probably seen FM radio stations around, like maybe from about 80 to like 120. Those are typically the frequency ranges that we'd expect. But we want to know that this is the same as 10 to the 6 megahertz. So we could rewrite this as 95.3 times 10 to the 6 hertz. It's not going to hurt you, but it might hurt you if you don't convert that mega into a number like this to just get the base SI, the base hertz. Okay, we generally want to convert all our prefixes. It makes life a lot easier. Okay, the second piece of information that we're given is the speed of light. So speed, we're going to use v. Maybe better be to say the velocity of light. It is given with high precision here, so we want to use everything that's given to us. 2.99792 times 10 to the 8 meters per second. Okay, now we are looking for the wavelength. This is our target. Okay, so the way that we want to address this question is with something beautiful called the universal wave equation. Universal wave equation. Okay, so essentially the universal wave equation is the velocity is equal to the frequency times the wavelength. Okay, yeah, it's actually it's fairly straightforward for this question. So we just have to isolate the lambda, which represents our wavelength, and well, that's just going to be lambda is equal to our velocity divided by our frequency. So let's do that math real fast. Let's sub in our numbers. 2.99792 times 10 to the 8 meters per second. And here we have 95.3 times 10 to the 6 hertz. Now, hertz is the same as saying 1 divided by seconds, or seconds inverse. So if you actually look at the units, they do cancel out just meters, which is very reasonable and what we'd expect. Okay, so I'm gonna send this through my calculator and find out what type of numerical answer this is gonna be. So with the maximum precision level, 2.99792 times 10 to the power of 8. Divide that whole thing by 95.3 times 10 to the power of 6 for megahertz. Do this calculation ASAP fast, and my calculation for lambda, our wavelength is 3.14577 meters, but we gotta worry about our significant figures. So we only have 3 significant figures that are available to us because of this a megahertz value. So let's convert this to 3 sig figs. So our lambda is going to be officially 3.15 meters. Now I know it's tempting to do 3.14 because, you know, everyone likes eating pie, but you know, if we're going to round this properly, it has to be rounded properly. So 3.15 is going to be our wavelength. Yeah, and we pretty much came to the same conclusion here. Just watch out for sig figs. So above solution is good. Good job. Cool. Okay, so here we have the next question on the menu today, and we have an electric circuit. Okay, I'm going to redraw the circuit real fast because there are some things that are not super clear in this diagram, so I just want to like make them more clear by redrawing this. So we have on the top, we have a resistor like this, 14.7 ohms. I have another resistor, 24.6 ohms. And here we have a voltage source. This has to be a voltage source. I've seen other diagrams that are kind of similar to this, so this has been a voltage source. And I'm going to assume that its plus is towards the right. So I would generally recommend against drawing voltage sources like this. Don't do that. They can get easily confused with capacitors. So instead, draw them like this, and you will never be confused, and you'll always know which side is positive. Okay, so let's just call this Vs for the voltage source, and it has an associated internal resistance on it, which is very realistic. Most real batteries or voltage sources have this. So in this case, 3.2 ohms. Here it mentions some nodes of interest. Here we have node Y. Here we have node X. It also gives us a current. I'm not sure why it gave us 2 arrows. Current is only allowed to flow in one direction, so the only way that the arrow could work out is like this. So here we have I, and that is given as 0.26 amperes. Okay, so the first question is, what is the EMF of the battery? Or another way you can say this is, what is the voltage of the battery? The first thing that we might want to do is simplify the circuit. So we know that the circuit could be a lot easier to deal with if we combine the resistors. Combine resistors. So our equivalent resistance, in this case, because we are in series, it's a whole different story when we have parallel resistors, but since we got the series resistors, we got something like this. So we just add up all the resistor values individually. So in this case, our equivalent resistance is going to be 3.2. I'll draw my units on the outside, plus 24.6 plus 14.7 all in ohms, and our equivalent resistance. Sending this to the calculator. Definitely should not trust yourself with math all the time. Verify with the calculator whenever possible. Mental math is cool and all, but you know, you don't want to get something wrong just because you mental math something out instead of calculating it. Okay, so my result for this calculation, 42.5 ohms. Okay, so given that we have our total resistance, we can redraw our circuit like this. REQ 42.5 ohms minus plus, this is our voltage source, and we don't know what it is, but that's what we're trying to solve here. And our current going through this circuit is I equals 0.26 amps. Okay, so to find the voltage, we want to do Ohm's law. Good old Ohm. And Ohm's law tells us that V equals IR. Or, actually that's exactly what we need, because we have our current, we have our resistance. The voltage drop of this resistance is just going to be IR, and the voltage drop of the resistance has to be exactly equal to the voltage supplied by the source. So in this case, we're just going to multiply them together. So here we got 0.26 amps multiplied by 42.5 ohms. So the result of our VS, voltage source, times 0.26, I'm going to expect around 10. It's going to be 11.05 volts. Pretty close on the guess, but you know, calculator is always right. So yeah, that would be our first answer. The electromotive force, the EMF, also known as voltage, is going to be 11.05. Came to exactly the same answer here. Awesome. Okay, part B is asking us, what is the magnitude of the potential difference VYX? So pretty much, given these nodes of interest, X and Y, what's the voltage between them? Okay, and it's asking us in units of voltage. Okay, so as we traverse here from X to Y, we can see that we're going to have the voltage source that's going to be added, and we're going to subtract the voltage absorbed by this resistor, and that's going to give us the potential difference between point X and point Y. So to do that, so that's going to be part B. Voltage between X and Y. We want to do, we'll call that VXY. So we know that this is going to be the voltage source minus the voltage drop of the 3.2 ohm. And we know through Ohm's law that this will be equal to RS for the source resistor or internal resistor. So subbing in our numbers, like we just solved for VS right here. So VXY, our VS value 11.05 volts. And we're going to minus our current 0.26 amps multiplied by 3.2 ohms. And that's the resistance value. Yep. So let's do that quick math ASAP fast and figure out what the result of that calculation is. 0.26 multiplied by 3.2, and my calculation result is 10.218 volts. Okay, and what this pretty much means is, since it was mentioned that this resistor is an internal resistance to the battery, that means that even if the battery was originally written to be you know, around 11 volts, its actual effective source voltage is going to be more like 10.2 volts. Okay, so that's why these internal resistances are are relevant. Okay, so that addresses part 2 of this question. And part 3 is asking us, what is the power dissipated by the resistance, by the internal resistor here? Okay, so part C. Power of internal resistor. Okay, so the power equation, this is a nice easy one to remember. I remember P equals I V, because I remember this by saying, like, potato is vegetable. You know, fairly straightforward. Potatoes are definitely vegetables. Anyways, so we're looking for our P value, and we're looking for our current that goes through our resistor, and we're also looking for our voltage. But we know that through Ohm's law that voltage is equal to IR. Okay, so we could write this as P equals I squared R. We know that the current going through there is 0.26. That's our I value. We've got to square that and multiply it by the resistance, which is 3.2 ohms. Yeah, fairly straightforward. So send that through the calculator, and this is a fairly straightforward answer. So 0.26 squared multiplied by 3.2. So the power that I got here, 0.21632 watts, represented with W. Okay, so that's the power. Cool, and hopefully we came to a similar conclusion here. Exactly the same and exactly the same. So just with some rounding, but otherwise everything is good. Everything is wild. This circuit is solved, and we are very happy with that. Awesome. So the above solution is good. Good job. High five. Okay, so here we have the next question on the menu today, and given this circuit, it is asking us what is the current in the 4 ohm resistor in the given circuit. Okay, so I'm going to actually redraw this circuit. My recommendation in general is that this is a better voltage source than this, because you'll see capacitors eventually if you continue down this electrical physics route, and capacitors are 2 parallel lines, so to avoid any ambiguity, draw them like this. Okay, so let's redraw the circuit. We got a 3 volts right here. Got a 2 ohm up here. Minus plus. That is a 6 volt source. Here we got a 4 ohm resistor. On this side, our plus is going upwards, and we got a 9 volter. And there we got a 8 ohm resistor. Okay, so essentially we are looking for this current right here. Let's call this IT for I target. And let's actually draw in some more currents, and then that will be very helpful with the power of some of Kirchhoff's laws to help us solve this circuit. So here, let's call this I1, or IL for I left, and this way, let's call this IR for I right. Okay, so just based off these currents that we like assumed directions for, we can say let's call this node A. Actually, let's call this the ground, because I think that we could do this quite easily with a nodal analysis. Cool. So given this, at the ground node, we want to use Kirchhoff's current law. So essentially what this means is incoming currents the sum of all incoming currents has to be precisely equal to the sum of all outgoing currents. Okay, so who's incoming to the ground node? Well, we only have IT that's incoming. Our target and outgoing, we want to add them all up, IL plus IR. Okay, so that's cool, but we know nothing about those currents, so it's not perfectly cool yet. But this is one of our equations. This is like an equation that we're definitely going to want to keep front and center in our mind. Yeah, okay, cool. So given this, to do a nodal analysis, we want to identify our other nodes of interest. So if this is our ground node, we know that this is going to be 0 volts. And let's just like identify some nodes here. So let's call this A, B, C, and D. Okay, so just looking at the diagram, we can see that between A and the ground, we have to pass a 3 volt source. Okay, so we know that A has to be 3 volts above ground. Ground is 0 volts, so A must be 3 volts. Okay, a similar type of analysis could be done for node C. So node C is 9 volts above ground, and ground is 0, so C has to be 9 volts. Okay, now here at B, we don't know the voltage directly, but we could calculate it using our current laws here. So one thing that could definitely be important to see here is Ohm's law. So suppose that we have I going this way, we have V1 and V2, and this is R. We know that I is equal to V2 minus V1 over R. Ohm's law. Okay, so we're pretty much going to want to apply this principle of Ohm's law just at this top node here, and we're just going to like substitute out these equations, these I values, for things that are with respect to voltage. Okay, so here VB, we don't know the voltage, but we can just say that this is VB, and that's going to be a variable that we're going to try to solve for. And once we get that, we can get to VD, the voltage at point D. And once we get that, VD minus VD divided by 4, that's going to be the current that we need. Okay, so substituting this out here, this actually may not be the best way to do this. Actually, another good way that we can do this is with loop analysis, because of this voltage source right here, it's going to make it a little bit tougher. Generally, you want like all resistors for this, but it's all a learning process. So another way that we can do this is with the loop analysis and Kirchhoff's loop law. I'm actually going to erase this so that it's not ambiguous at all. So the sum of all voltages in a loop will always be 0. Okay, cool. So let's say that this could be loop 1. And here could be loop 2. So in loop 1, we know that our voltage has to be 0. So we're gonna do it like this. So this can be voltage sources. The sum of all voltage sources is equal to the sum of all voltage drains. Okay, so the voltage sources, as we traverse this loop, we got a 3 and a 6, right? Yeah, okay, so we have a 3 volt plus 6 volt as voltage sources, and for voltage drains in this loop, we have IL times 2 ohms. And we have another current here, another resistor, our 4 ohm, and that is times IT. And we're trying to solve for IT, but we'll eventually get there. So we got IT, our target, multiplied by 4 ohms. Okay, now let's look at the second loop. Okay, so keep in mind the direction of our loop. All of them are going clockwise for us here, and that is very important for the which part of the voltage source we're entering. So if we're entering the negative side, that means it's a voltage source, but if we're entering the positive side, that means we're a voltage giver or a voltage drain. Yeah. Okay, so our second equation, we got, our second loop, let's start up here. We're going to have IR, negative IR times 8. Actually, it might be easier if we do our loop the other direction. So here we'll have 9 volts and 6 volts as our sources. As our sources, and as our drains, we shall have IR times 8. And we will add up IT times 4 ohms. Okay. Interesting. Okay. So let's actually let's simplify these equations a little bit. I'll give this a little bit more space by moving it down. So here we can hopefully clearly see that this will be 9. Whoops, that's not Q. 9 volts is equal to 2IL plus 4IT, and here we'll have 15 volts is equal to 8IR plus 4IT. So here we're going to have a system of equations. Keep in mind our original. So let's write out our system of equations. So our first one, when we bring everything to one side and equate this to 0, we'll have IL plus IR minus IT is equal to 0. Minus IT is equal to 0. Our second equation is going to be 2IL plus 4IT and that's going to be equal to 9. And our third equation is going to be 8IR plus 4IT is equal to 15. Okay, 3 equations, 3 unknowns. This is solvable. And what we can do is I'm going to put this into my matrix calculator on my calculator. Let's find that ASAP fast. Oops. Oh man, where is that? Okay, 3 equation, 3 unknown. And so I got 1, 1, -1, 0, 2, 0, 4, 9, 0, 8, 4, 15. And solving for this, I got IL is equal to 0.857 amps. IR is equal to 0.964 amps, and IT, which is the sum of both of them, shall be 1.82 amps. Okay, now we were looking really only for IT, so that will be our final answer here after we send this through our equation. Yeah, seems moderately reasonable for an answer. So this calculation is a little bit sketchy to me because these currents seem very, very high, like 3 volts and 2 ohms. I would expect I wouldn't expect to see like 15 amps in here. So I feel like my answer feels a little bit more right because here like we have 6 volts, maybe plus a little bit. So I wouldn't it's certainly within the realm of possibility to have like around 8 volts here and then divide by 4 ohms to get almost 2 amps. I feel like this feels more right because the currents here are too big, so it's kind of important to kind of develop like, you know, the ability to like smell check when numbers feel right, because when they feel right they most likely are right. Okay, so the above solution is incorrect. The current is way too high for that arrangement. Oops. Of sources actual current is 1.82 amperes. Okay, so likely just an algebra problem, or maybe setting up the loops, but yeah. Okay, so here we have the next question on the menu, and it is asking us, or is presenting the situation where we have a diatomic gas originally with a volume of 2 cubic meters, a pressure of 200 kilopascals, and a temperature of 50 degrees Celsius. The gas expands isobarically to a volume of 3 cubic meters. Now it is asking us what is the work done on the gas by the process, the final temperature, and the heat transfer of this gas as this process occurs. So the first thing that we need to address here is, what does it mean by isobarically? Okay, so isobaric expansion, what's going on here is that the pressure is constant as the volume increases. Now, assuming that there is no additional material added to it, no additional gas added, the temperature has to increase to keep the pressure constant. Because as things get more hot, their pressure increases, right? Because gases expand when they are at higher temperatures. So the hotter that it gets, the more outwards pressure it's going to be. But if the volume increases, the increase in volume must be happening in parallel with an increase in temperature in order to keep the pressure the same. So the volume increases and temperature has to increase. Those two things have to happen at the same time for the pressure to stay constant, because increasing the volume reduces pressure, but the temperature increases the pressure. So you're kind of balancing those two things at the same time. Okay, so let's actually write down our givens. So our volume 1, or our VI, for initial volume and our final volume. So our initial volume is 2 cubic meters. Our final volume is 3 cubic meters. That is actually fairly large. 1 cubic meter is about the size of, or about the volume of a human, to be honest. You could hide in a 1 cubic meter box if you wanted to. So these are fairly large volumes. The temperature initially is equal to 50 degrees Celsius, but we want to convert this to Kelvin. So 50 plus 273 Kelvin. So 273 plus 50 is 323 degrees Kelvin. And our final temperature, we don't really know that, so we'll probably need to find that eventually. And our pressure is 200 kilopascals. Or another way that we can say that is 200 times 10 to the 3 pascals, just to have everything in base SI, which could be useful. Now, the equation that we want to use here is this equation right here for the work done. So work done is represented with W for work, makes sense, and is going to be the pressure times the change in volume. So V1 minus V2. Now the reason why we're doing V1 minus V2, is because normally when you do like change in things, you're doing the final minus the initial. The reason why we're doing it this way is because the question, now this is where precision of language gets very important. The question is saying, what is the work done on the gas? It's not the work done by the gas, because the gas would be doing work to be increasing its volume and its temperature. But since it's the work done on the gas, we're actually doing like negative work, okay? So we're going to expect a negative result. Like the magnitude would be the same doing either way, but we want to set it up this way so that our sign is going to be negative, because there's negative work done on the gas, positive work done by the gas. Okay, so subbing in our numbers, we get 200 times 10 to the 3 pascals multiplied by 2 cubic meters minus 3 cubic meters. So we could just write that as 2 minus 3, that's just negative 1. So it'll just be negative 200 times 1,000 joules, or 200 kilojoules. That could be another way to say it, but yeah, this would be the work done on the gas. Not sure why they mentioned by the gas though. Okay, interesting. Now the second part of the question is asking us, what is the final temperature? Now to find the temperature, we want to use this relationship, because the volume and the temperature are very closely related. Like I mentioned before, if the volume is increasing, that decreases the pressure. And the temperature has to increase to keep the pressure constant. Otherwise, it's not isobaric, which is one of the conditions of this question. Okay, so for part B, we know that our relationship is going to be our final temp over our initial temperature. The ratio between our final and initial temperature has to be the same as the ratio between our final volume and our initial volume. So if we're trying to solve for our final temperature, we got to do our final volume divided by initial volume multiplied by initial temperature. And final volume, that is 3 cubic meters divided by 2 cubic meters multiplied by 323 kelvins. 323 kelvins. So 323 times 1.5, another way of saying 3 divided by 2, 484.5 kelvins. Okay, so that shall be our final temperature of the gas upon its isobaric expansion. Cool, and yeah, probably exactly came to precisely the same answer here. And the last question is, what is the heat transfer into the gas? So the heat transfer is going to be the same as the work that we're doing, because like all the work that is done on the gas is becoming the heat. As we're increasing the volume, any energy that we're adding to it is just going to like it's just going to be heat. So all the heat transfer is going to be the same as the work done here. So it's going to follow the same procedure as calculating it with this equation. So that shall give us our the amount of heat energy that is put into the gas. Now, if it told us, and I guess we also know the final and initial temperatures. So if we wanted to, we could calculate like the, some of the heat properties of the gas itself and maybe use that to help us identify it. But that is not part of the procedure, so we don't really need to worry about that. Or not a part of the question, so we don't need to worry about that. And yeah, so this solution is good. Okay, cool. So this is the next question that we got on the menu today. It is presenting this situation where we have a point charge called Q at the origin. A particle of mass 2 grams carries a charge of 15 microcoulombs. The particle is released from rest at x equals 1 meters, and its kinetic energy as it passes 25 centimeters is 0.5 joules. What is the charge Q? Okay, so let's actually draw a diagram to represent the situation here. Keep in mind here it says 1 meter and 25 centimeters. Okay, that's a very important thing because otherwise we would have a very wrong answer. Okay, so keep that in mind. So let's draw the situation. We have our point charge Q, and this is at x equals 0. Oops. Okay, so let me just draw out what I imagine 1 meter might look like. Oops, can't count these grid lines. Okay, so this would be 1 meter, and this would have to be 0.25 meters or 25 centimeters, and this is 1 meter, this is 0 meters. Okay, so these are the distances, and we have a particle that initially starts at x equals 1. We have our mass is equal to 2 grams, which is equal to 0.002 kilograms. And our charge is 15 microcoulombs. Another way that we can write that is Q is equal to 15 times 10 to the negative 6 coulombs. And here we are starting at rest. Okay, so our initial velocity, our VO, is 0 meters per second. And once we get to here, like we're moving at this point. Oh, also the charge is negative. Whoops, that's my bad. Oops, I'm gonna need to find a nice way to give myself some space. Okay, so when we get to this point, it has a kinetic energy of 0.5 joules. Okay, so these are all of the things that were given. This is a pretty good representation, and we're trying to solve for Q. So essentially what we need here is our we want to be thinking in terms of energy, right? Because we were given an energy value, and we know that we have you know, a lot of things that could help us lead to a bunch of energy values. So that's the way that we want to proceed with this. We want to think about the conservation of energy. Okay, so in this case, it's all going to be, we have our initial potential energy, so PEI, plus our initial kinetic energy, but we actually don't have a kinetic energy. 0 starts at rest. And we're going to equate this to our final potential energy, PEF, plus our final kinetic energy. And we're already given our final kinetic energy, so we don't really need to calculate that. I mean, we could if we wanted to, but we could also calculate the speed if we wanted to, but that's not what the question is asking, so let's just focus on what the question is asking. So let's, pretty much is just going to be the change in potential energy that results in this kinetic energy popping up. So we want to sub out some of these equations so that or some of these terms to get their actual equations. So we know that the potential energy of a charged particle is going to be kq over kqq over r. Okay, that's the potential energy. So let's call this RF, and this will be RI for our final distance and our initial distance. So our initial distance will be our initial potential energy, kq big Q little q over r initial, is going to be equal to k big Q little q over r final plus well, simply 0.5 joules, because that's what was given to us in the equation, and we're trying to solve for big Q. Okay, and we know that big Q has to be positive, because since a little q is negative, they're going to need to be opposite signs so that little q is attracted to big Q, because they're getting closer to each other. Okay, so let's bring this term to the other side of the equation. So we're going to have k big Q little q over Ri minus k big Q little q over Rf is equal to 0.5 joules. And we want to factor out big Q, because that's what we're looking for. Oops, so let's make this J a little bit more pretty. Okay, so we'll actually factor out the K and the both Q's. K big Q little q 1 over Ri minus 1 over Rf equal to 0.5 joules. And to isolate for a big Q, we will need to have 1 over k little q times 1 over Ri minus 1 over Rf times 0.5 joules. Okay, so let's sub in our values here. 1 over 9 times 10 to the 9. That's our K. Our Q value was negative 15 times 10 to the negative 6 coulombs. Our initial was 1 over 1 meter minus 1 over 0.25. That's our final distance. And on top here we have 0.5. Yeah, just that. So let's run through this calculation. So 9 times 10 to the power 9 times 15 times 10 to the power of negative 6 times 1 inverse minus 0.25 inverse the reciprocal of that times 0.5, and my result for this is a positive value 1.23456. This is too perfectly set up. 1.2345679 times 10 to the negative 6 coulombs. That's like way too perfect of an answer. That's pretty beautiful. And since we have it came out to a positive, so we can actually rewrite this as Q is equal to how many significant figures do we have here? So we got one significant figure here, so unfortunately we do got to cut this off at just like 1 microcoulomb, positive 1 microcoulomb to 1 sig fig. Okay, so that would be the answer, and it has to be positive because it's attracting the negative charge into there. Okay, so yeah, cool. So sign error. Answer is good, just needs to be positive. Cool. Okay, so here we have the next question on our menu today, and it is presenting us with the following situation where in the figures below, assume that each velocity vector is actually replaced by a wire carrying current in the direction of the velocity vector. Okay, for each case we need to find the direction of the magnetic field that will be produced, that will produce the force as shown. Okay, so I'll redraw these diagrams when we get there. The main principle that we want to apply for this situation is the magnetic force and moving charge equation. So the equation looks like this. F is equal to Q times the cross product of the velocity, cross product the magnetic field. Force, charge. But since we're just worried about the direction, we don't really need to worry about actually doing the calculation. It's just kind of it's good to know who everyone is. Here we have a velocity of charge. Here we have magnetic field. Okay, now keep in mind this is a cross product, right? So due to the fact that it's a cross product, we have to follow our right hand rule. Hopefully you have a right hand with you. So if I draw out a hand like this, and like this is the palm of your hand, so you know you might have your lines here. Your velocity, same as fingers. Maybe I'll do that a different color. Your magnetic force of palm. It's kind of like, you know, if you were like, you know how Iron Man like shoots lasers out of his hands like this. That's like what the B field is going to be. And our last one is our force is going to be the same as thumb. Okay, so if that's your right hand, this is like how you want to apply it. And let's take a look at these situations here. Okay, so our first situation is we have our velocity going this way and our force going upwards. So if our velocity has to follow our fingers, our force has to follow our thumbs, our palm is pointing into the page to follow the right hand rule. So B field is going into the page. We can kind of represent this as like I know in chemistry we represent it as like, you know, it starts out big, then it eventually gets smaller. So that's the direction of the B field. into page. Okay, so this would be our part A. Our part B, okay, yeah, part A is into the page. That's awesome. Part B is like this. So we have our force still going upwards, and our velocity is coming out of the page. So we can kind of maybe it'd be all right to represent it like this. So this is our force. This is our velocity. Now I know that the question mentioned that the velocity vector can be replaced by a wire carrying charge. That would be the same as velocity, because it's the movement of charges themselves. So current is just the movement of charges, so you know it would be the same thing. So since this is coming out of page, you know, with our V, our fingers coming out of the page, our thumb going upwards, our palm, where our B is pointing, has to be going towards the right. Our magnetic field is towards the right. Okay, so this would be our B situation. To the right. Awesome. Okay, and our final thing is going to be our C. So let's see what C is all about. We have our force going towards the left, and we have our V going into the page. Okay, so I'll represent it like this. Okay, so following the same procedure, our fingers going into the page, our thumb going towards the right, our B field is going down for real. Okay, so it's got to be going down. That's the only way that this could work. P field. Only way this could work with our right hand. Don't use your left hand rule unless you're using like negative charges, but yeah, don't. Typically, you're going to want to stick to your right hand rule. It's your right hand, it's your go-to. You know how it goes. Okay, and the last one is going to be straight down, going down for real, and that's all good. So following the right hand rule, that's awesome. Okay, so this solution is good. Good job. High five with the right hand. Okay, so this is the next question that we have on the menu today, and it's presenting us a situation where we have Jane, who is 50 kilograms, needs to swing across a river filled with crocodiles and velociraptors. Dinosaurs are coming back, and she's trying to rescue Tarzan. And Tarzan is a little bit heavier at 90 kilograms. So she must swing with a constant horizontal wind force that is applied to her. Oh, this is the diagram that represents it. So as Jane starts here and she swings over, the wind is trying to blow her, you know, the wind is working against you. Working against Jane in this case, as she's swinging there. And it's initially set at an angle theta with the vertical. Theta is given as 50 degrees. And we also have a couple distance vectors or values. So the separation of the river, 50 meters, and the wind force is 150 newtons, and the length of the rope is 40 meters. Okay, cool. So let's draw out the situation. Let's actually think about this question first. So what is the minimum speed that Jane must begin her swing with in order to make it to the other side? And the hint that we're given is that we got to work with energy, which is cool. I always feel energized with the energy. Nothing to be worried about. Okay, cool. So let's redraw this out in a more abstract way. So we know that we have situation comes to us like this. Here we have theta, which is 50 degrees. This length here, we have L. That was given as 40 meters. that starts up here. Jane is 50 kilograms. And coming this way, we have a different angle. Here they represent that with the letter chi or phi. Now I don't think we're given phi. Yeah, I don't think we're given phi, so we'll probably need to calculate it, which is nothing to be too worried about. Okay, no worries. And here we got Tarzan. Let's just say TZ. Tarzan from Tanzania. The Tarzan was 90 kilograms. The distance between them here is 50 meters. Okay, so the first thing that we're going to need to consider here is that we do have an unknown height difference that we definitely need to take care of. So this is h. Now, we do need to do a little bit of trigonometry to figure out what in the world that is going to be. So if we look at this diagram right here, we could figure out, knowing the hypotenuse, what this distance is with some trigonometry. So that is going to be 40 meters times cos 50. And we know that 40 meters is going to be h plus this distance right here, because that's going to be the swing. Yeah. And oh, this should be like from the base, because we're going to come up a little bit as we get back to Tarzan's side. So this, maybe just to be 1000% clear, I'm gonna just redraw this like this. Lowest point of swing. Okay, cool. So we know that 40 meters, which is the length of the 40 meters is the length of the rope itself, and at its lowest point, and at its lowest point it's going to be this height, which is 40 cos 50. Don't really need the units here. Plus h. Okay, so isolating for h, we're going to have h is equal to 40. Factored out the 40 is going to be 1 minus cos 50. 1 minus cos 50 degrees multiplied by 40 meters. We got 14 meters. 14.3 meters. Okay, this will be our h value. Now this h value here is going to be useful Okay, it's actually a fairly tough question. Okay, so we're gonna follow the same procedure on the other side to find this angle right here, because that's going to be quite important, because we need to know, like, not just the distance between them and the ground, we need the distance between them and each other, or not the ground, between them and the lowest point. So if maybe I'll do that in a different color. Let's do green. Okay, so this height here, let's call this HT, height of Tarzan. So height of Tarzan is going to be L minus cos chi L again. Not chi, it's phi. And so this shall be, now we don't know phi right now, so we're going to need to leave that, but it's going to be 40 times 1 minus cos phi, like that. Okay, now for these distances, so maybe I'll do a different color for this, perhaps blue. So let's call this dj for the distance between Jane and the lowest point. And here we're going to have dt for Tarzan's distance. Okay, and those are just going to be trigonometries as well, except we're going to use sine instead. Okay, so dj is going to be equal to 50 sine 50 times L, which is 40 meters, okay, so I'm going to calculate that real fast. Sine 50 times 40, 30.64 meters. Okay, and dt, the distance between Tarzan and the center when the lowest is going to be, well, is going to be sine phi times 40. Times 40. And we don't know what phi is, but we know that 50 is the sum of dt plus dj. So solving for dt, we know that this is going to be equal to 50 minus 30.64 meters. And that will be equal to sine phi times 40. So phi will be equal to 50 minus 30.64. So I'm going to do that real fast. (19.36) over 40. Oops, all of those need to be passed to inverse sine, or arc sine, if that's more your style. It's probably more safe to say arc sine. Okay, so arc sine of 19.36 divide 40 is equal to 20. Oh, I have the distance, but I need the angle. So I need to inverse sine that. Oh yeah, it is 28 degrees. Or 29 degrees, just to round it. Okay, so let's put these onto our diagram. So here we have 30.64 meters. dt it's going to be 29.36 meters. H is going to be 14.3 meters, and HT, now that we have phi, we can calculate that. So let's go back to green. One minus cos 29 degrees calculating that ASAP fast. So here I got h of t 5 meters. Okay, so I'm actually going to redraw this diagram ASAP fast because actually no, I think we're good. So this will be 5 meters. Okay, so as we can see, if Jane just swings here, she's gonna go as far as she can. Like she's gonna gain a lot of kinetic energy because she's gonna end up lower than where she is. But keep in mind, we have a constant wind force going this way. So Fw for F wind, and that is equal to 150 newtons. Oh, you can't even see that I was writing. Okay. So here, F wind is equal to 150 newtons. Whoops, not W's, newtons. Okay, and we know that the work done by wind is going to be 150 newtons, because it says it's going to be constant, and we're going to multiply it by the distance at which it's going to be applicable, right? So it's going to be for 50 meters. So 150 times 50 meters is equal to 7,500 newtons. I mean joules of work. Okay, so that's the work of wind. Okay, so now that we have all of these, now that we have this diagram complete and all the work and all that, we can kind of start moving towards actually calculating Jane's journey and what we should do in response to that. Okay, so as you can kind of see from the diagram, as Jane goes down, like she's going to lose some height, and she needs, and because she's losing height, she's losing gravitational potential energy, and she's also gaining kinetic energy as that happens. Now the energy, another thing that we kind of need to keep in mind is that once she arrives to the other side to rescue Tarzan, she's got to have a velocity of 0, otherwise she's gonna like kick him in the face. Like she's hopefully gonna try to get there with a velocity of 0. So we're basically looking for the kinetic energy of Jane plus the kinetic energy gained from the gravitational by reducing her height and on that swing, that has to be perfectly balanced with the work of the wind to make it so that her energy as she gets here is going to be a 0, or her velocity as she gets there will be 0, so no kinetic energy. Okay, so let's set up that equation like this. So conservation of energy is our key concept. So we have our initial kinetic, so KEI for initial, plus our potential energy initial is going to be equal, or it's actually going to be our change in potential energy, because up here you're going to have a certain degree of mgh of potential energy, and down here you're going to have less. So it's going to be the change. It's not going to be your absolute potential energy. That's going to be like extremely large. It's our change in potential energy. That is going to be completely equal to the wind force that is applied here. So that's going to be our work of wind. Okay, so our initial kinetic, to change these into equations, we'll do it like this: 1/2 mv squared plus mg times delta h, the change in height, and that's going to be equal to 7,500 joules, because that's what we calculated as the work as done by wind. Okay, cool. So given this, we just need to solve for v. Okay, so let's do some algebra ASAP fast to solve for v. So I'll actually go back to writing WW just to make this a little lighter. To write minus mg delta h is equal to 1/2 mv squared, multiply both sides by 2 over m, equals 2 over m of WW minus mg delta h, and our velocity is just going to be this whole thing under the square root. Okay, copy pastas, definitely helpful. Okay, so subbing in our numbers here, we are gonna have 2 over Jane's mass, so 50 kilograms, multiplied by the work done by the wind, 7,500 joules, minus Jane's mass, so 50 times 9.8, and this is the change in height, so we have to find, so it's really just going to be like 14.3 minus 5 equals 14.3 minus 5 meters, and that is 9.3 meters. Okay, hopefully that's what we calculated here as well. I'm going to assume that's going to be caused by a rounding error, but it's pretty much the same. They went with Pythagoras. I mean, it's close enough to where I'm just going to assume that that's a rounding error, but we'll go with 9.3. So times 9.3 meters, all under the root. Okay, so let's math that out ASAP fast. Okay, so under the root we got 2 divided by 50 multiplied by 7,500 minus 50 times 9.8 times 9.3, all under the root, and I calculated the initial velocity needed to be 10.85 meters per second. Okay, so initial velocity required to cross the river. Okay, cool. So that would address part A. Came to the exact same number here. That's awesome. It's just like the way that this question is set up is kind of spooky, but we'll talk about that later. Okay, so part B of this question is asking us, now they're trying to go backwards. So Tarzan and Jane are trying to swing back to go the other way. Okay, so what is the minimum speed that they need to make that possible? So now we got this, now we want to set up the equation in a different way. So part B, still the same situation, the same setup, the same forces and everything. So here, let's pay attention to the wind. The wind is going towards the right. So in this case, the wind is going to be helping us. And we're also going to try to arrive with a zero kinetic energy. Okay, and we also need to keep in mind we need to increase our potential energy because we are getting higher up. So all of our kinetic energy is going to be converted into gravitational potential energy. So really what we have here is our initial kinetic energy plus the work done by wind is going to be equal to our final potential energy, or our change in potential energy, which is mg delta h. Now keep in mind here, now we have both people on the rope now. So our mass is going to be 50 kilograms of Jane plus 90 kilograms of Tarzan, for a total of 140 kilograms of friendship. Cool. So let's turn these equations into, or turn these symbols into equations. So here we got 1/2 mv squared plus the work done by wind is equal to mg delta h. Should have wrote potential energy. Whoops. Nothing to worry about. And we just got to isolate for v once again. So we shall have v is equal to, under the roots, we have 2 over m multiplied by mg delta h minus the work done by wind, all under the root. Okay, cool. So let's sub in our numbers. 2 over our combined mass, so that's 130 kilograms, times 130 kilograms, times 9.8 meters per second, times our change in height, which was 9.3 meters. It's the same change in height, minus 7,500. That's the amount of joules, the work done by the wind. So let's calculate this out and see what we get. Okay, so under the root we got 2 divided by 130 inverse, divided by 130, my bad, times, in brackets, 130 times 9.8 times 9.3 minus 7,500, close the bracket, and my result for this is 8.18 meters per second. Velocity required to return. Okay, hopefully we came to a similar conclusion down here. About 8, I'm going to assume that these are just rounding discrepancies. Or I am actually tripping by writing 130 instead of 140. Jeez. Luckily in my calculator, that's a very easy thing to recalculate. That's very bad of me, so stay ready to avoid things like that. Yeah, I did actually calculate 8.66 as well. Meters per second, and that would be the velocity required to return across that chasm. Okay, so I would call this a question complete. My only concern is some of these equations are set up funny, but otherwise everything's good. So equations are set up funny, but otherwise the correct solution is found. Nice. Oh man, so that was the last question that we have. Unfortunately, time flies when you're having fun, as the old saying goes. So those are all the questions that we have today. If you enjoyed today's Q&A and would like to be notified of when we do this again, please hit the subscribe button and ring the notification bell below. Yeah, ring the notification bell and subscribe if you really enjoyed the video. If you're interested in submitting your own questions, please visit the links in the description below. Leave a like and a comment, and if you really enjoyed the video, share it with your friends. This has been Millan from OneClass. Today was a great time with the physics. I hope you have a great day, and I hope to see you again soon on our next OneClass live stream. Take care and have an amazing night, or day, or afternoon, whatever time it is for you. Enjoy yourself, enjoy the physics, and stay safe and take care.